Hello. This will be a demonstration of Proposition 8 from Book 2 of Euclid's Elements, which states that if a straight line be cut at random 4 times the rectangle contained by the whole and one of the segments, plus the square on the remaining segment, is equal to the square on the whole plus the said segment. Again, these Book 2 enunciations, nightmare to understand without an example. So let's make our example. All we are given is a straight line AB, this straight line right here, cut randomly at point C. The reason I've pre-drawn the diagram is because it's a mess, and I have to remember all the letters up to U, and I don't want to do that. So, given that we just have a straight line AB cut at random at point C, what we are going to prove is that 4 times the rectangle contained by AB and BC, this is the whole and one of the segments, AB being the whole and BC being one of the segments, plus the square on the remaining segment. So the segment we decided to choose was BC, so that makes AC the remaining segment, and so we're going to add the square on the remaining segment, the square on AC, and that is all going to equal the square on the whole plus the said segment. So the square on the whole plus the said segment means that we're going to take AB and we're going to add BC to it and then draw a square on it. So the square on that whole length, AB plus BC. That's A plus AB plus BC squared. Okay, so first thing we're going to do, this will actually be a little different from our usual Book 2 constructions. We're going to extend the straight line BC to point D such that BD is equal to CB. We haven't done this in a while. This is postulate 2 to extend a finite straight line continuously in a straight line. And then from there, we use 1,3 to make that extended straight line equal to something. I actually forgot to write that in my reasons. That's okay. Next, on this whole straight line, AD, which we've now created by extending AB to point D, we're going to construct the whole square AEFD. We did this by proposition 146. And now, just as with the last proposition, we're going to simply let the figure be drawn. The figure being, when you have a square, what you do, connect one of the diameters, so we join the straight line DE, and then we draw various parallel lines. What makes this different from the usual figures we've seen is that we do this twice. So we first do it drawing the straight line parallel to the sides of the square through B, and then where BL intersects with the diameter of the square, we draw another parallel straight line. And likewise, through point C, we draw a straight line parallel to either of these sides of the square, and then where the straight line CH intersects the diameter DE, we draw more parallel lines. So that is what Euclid means by let the figure be drawn double. Again, our whole construction is done in one step. Now, we know that CB is equal to GK. We know this because they're opposite sides of a parallelogram. This is proposition 134. We also know that BD is equal to KN for the same reason. We can then say by combination 1 that GK equals KN. So this straight line is equal to that straight line. This straight line is equal to that straight line. So these two straight lines are equal to each other. Similarly, we can prove that QR and RP are equal to each other. This is because BC is equal to QR because of proposition 134 again. We also know that we also know that BD is equal to RP, and so we can say that these are equal to each other because BC and BD are themselves equal. We made them that way. Next, we know that the parallelogram CK is equal to the parallelogram KD. This is because they are on equal bases, CK on BC and DK on BD. and they're in the same parallels. We simply made the straight line MN, which contains GK and KN, parallel to AD, which contains BC and BD. And so by proposition 136, that parallelograms on equal bases and in the same parallels are equal, we can say that the parallelogram CK is equal to the parallelogram KD. Likewise, we can also say that the parallelogram GR is equal to the parallelogram RN, again, by virtue of proposition 136. We can also safely say that the parallelogram CK is itself equal to Rn. This is because they're complements about the diameter of a parallelogram. This one's a little bit harder to see, so I'll take it out. The whole parallelogram we will be talking about here is CP, and we have its diameter dq. So this whole parallelogram CP, and its diameter dq. The complements are CK and KP, or Rn, whichever way you would wish to describe it. Because these are complements in a parallelogram, they're equal. So CK, the parallelogram CK, is equal to the parallelogram Rn. Then again, by common notion 1, we can say that KD and GR are equal because they're equal to equal things. And so we saw this in the last proposition as well with, I believe, rectangle AF and CE. Not confident that those are exactly the rectangles, but I think that might be right. Where we have multiple equal areas, and we say that they are a multiple of one of the areas. So if we add 4 equal areas up, it will be quadruple of one of them. And so in this case, if we add CK, KD, GR, and RN, they will equal quadruple of the parallelogram CK. This is common notion 2, a little bit different, but it's the same thing. Next, that's funny that I wrote it out like that. CB is equal to BD. We made it that way in the first step. BD is equal to BK. This is because of the porism of proposition 2.4. We know that the parallelogram KD is a square, and so all of its sides are equal, and BK and BD, being sides of a square, are equal. We also know that BK is equal to CG. This is by proposition 134 again. These are opposite sides in the whole parallelogram CK. We also know that CB is equal to GK, again because of proposition 134. And we know that GK is equal to GQ because of the porism in proposition 2.4 again. We know that the parallelogram GR is a square, so its sides are equal. Oh, I'm lost. I'm not lost. We can then say that we know that GQ is then equal to CB. We also know that CG is equal to CB, and so we can say that both these things are equal to each other. This is common notion 1. And so CG is equal to GQ. CG is equal to GQ. We also know from step 2 that QR and RP are equal. And now we say that the rectangle AG is equal to the rectangle MQ, and the rectangle QL is equal to the rectangle RF. How can we say this? This is proposition 136 again. It's a little bit more difficult to see this time, but it's there. We have equal bases, so we know that CG and GQ are equal, and they're in the same parallels because CQ is parallel to AO. We made it that way. And so we can say, by virtue of Prop 36, or Prop 136, that parallelograms on equal bases and in the same parallels are equal. We can say that the parallelogram AG is equal to the parallelogram MQ. Similarly, we can say that the parallelogram QL is equal to RF, because QR is equal to RP, and QP is parallel to HF. Okay. Awesome. We also know that the parallelogram MQ is equal to the parallelogram QL. This is again by proposition 143. These are complements in the whole parallelogram ML. And so we can say that they're equal. And so using common notion 1 again, we can say that the rectangle AG is equal to the rectangle RF. That's my bad. RF. Okay, so AG is equal to RF, because RF is equal to QL, and AG is equal to MQ, and MQ is equal to QL. Just lots of common notion 1. Okay, and again, we can say, by common notion 2, we saw this in the previous step, step 3, that if we add the rectangle AG plus MQ plus QL plus RF, we get quadruple the rectangle AG. Furthermore, we know that the 8 areas, I simply wrote 8 areas because that's 8 areas, I'm not writing that. The 8 areas being referred to are CK, KD, GR, and RN. So these 4 areas right here, plus the 4 rectangles, AG, MQ, QL, and RF. All of those areas we can see compose the whole gnomon STU. STU being this, was that, was that. If we were to do this as a proper, like usual gnomons, the 3 areas this one contains are AQ, the square CP, and QF. And so these 8 areas compose the gnomon STU, and we know it is 4 times the rectangle AK. This is because the rectangle AK is equal to AG plus CK. And so if we add, so if we add AG to CK, we also add MQ to GR. We can add, let's say, KD to QL. We can add RF to RN. And then by common notion 1, we know that the sums that we'll get thereafter will also be equal. And so yeah. So the whole gnomon STU is quadruple the rectangle AK. Because we can combine the 8 areas of the gnomon STU such that they all equal the rectangle AK, and we can do that 4 times with the 8 areas. And so we can say that the gnomon STU is equal to quadruple the rectangle AK. We also know that the rectangle AK is contained by AB and BK. Right, we have the right angle right there. So the rectangle AK is contained by AB and BK. We know that BK is equal to BD because these are 2 sides of a square, porism of 2, 4 again. And so we can say that the rectangle AK is equal to the rectangle contained by AB and BD. And so substituting that in for what we just saw with the gnomon, we can also say that the gnomon STU is equal to quadruple the rectangle AB, the rectangle contained by AB and BD. So the rectangle AB times BD is equal to the rectangle AK. Next, we will add equals to equals. So we shall add to the gnomon STU the square OH, OH being the square right here. We know that this square OH is equal to the square on AC because AC is equal to OQ, opposite sides of a parallelogram, Prop 134. And so we can say that the square OH is equal to the square on AC, is AC squared. And so we can say that the gnomon STU plus OH equals quadruple the rectangle contained by AB and BD plus the square on AC plus AC squared. And because BD is equal to BC, this again calls us all the way back to step 1, and that BD is equal to BC, we can substitute one of the containing sides for its equal, And so we can also say that the nomon STU plus the square OH is equal to quadruple the rectangle contained by AB and BC plus the square on AC. Next, we also know that the rectangle AD is equal to the rectangle, we know that the straight line AD is equal to AB plus BD. This is simply self-evident. And we know that BD is equal to BC. We made it that way, and so we can safely say that AD equals AB plus BC. And so we can substitute the AD in this step right here, this AD right here, for AB plus BC. And so we can say that the square on AB and BC is equal to 4 times the rectangle contained by AB and BC plus the square on AC. And this being what was set out to have been proven, we're done with the proposition, therefore, etc. QED. I do not have much of a commentary. Not even much of a commentary. I don't have any commentary on this proposition. So I'm simply going to end it here, and we'll move on to 2.9.